Simultus Functional Training, Part 8, Moving in the Coordinate Systems. After defining the kinematic relationships and connecting 3D solids to the coordinate systems, we will deal with moving the elements of our device, that is, moving previously created coordinate systems. Simultus allows controlling the position of the coordinate system during simulation by changing the value of the register at the input of the associated function block 6DOF axis. We'll get into the subject by using an example of a forklift. It is controlled with a gamepad, but we will focus on the kinematic relationships and movement of individual coordinate systems of the forklift. The main coordinate system is the body. All wheels and the forklift mechanism are attached to it. It can move in the horizontal XY plane and rotate around the vertical axis. Therefore, the control signals were connected to the X, Y, and ROT-Z inputs of the 6DOF axis block. The front wheels are attached directly to the body. Three jointly moving solids are connected to the left front wheel system: a wheel hub, rim, and a tire. In the diagram we only control the rotation of this wheel. The control signal is connected to the ROTY input, as the wheel turns in relation to the body in this axis. The kinematic relationship can be seen in the tree and in the 3D view. The LP wheel system is connected to the body with a black line. The rear wheels are swiveling. That is why in our model we first defined swingarm systems, turning in the vertical axis. Only after that, we connected them to the coordinate systems of the wheels, which are rotating like the front wheels in the y-axis. The 3D solids of the wheel, rim and tire are connected to the latter. In the diagram, the swingarm system will be rotated in the z-axis and the rear wheel system in the y-axis. Kinematic relationships should be analyzed in more detail in the case of a lift. The lifting frame is attached to the body. This is the case in a real device, and it's also indicated by the construction of our tree. The frame can tilt relative to the car body in the y-axis, so it is controlled only in the y-axis as well. The lift itself works in two stages. The first stage is attached to the frame, and the second stage is attached to the first stage. Both stages will be moved in the vertical axis. The control signals are connected to Z inputs in this case. The forks, in reality and in our model, are attached to the second stage and move sideways along the Y-axis. They can be moved independently, so we can define two coordinate systems for them. The forks on the diagram are controlled by connecting the control signal to the Y inputs. In this case, please pay attention to one important thing. Almost all coordinate systems that we have discussed so far are controlled by separate signals connected to 6 DOF axis function blocks. If possible, use only one function block input to control the motion. However, by creating a tree of kinematic relationships, we obtain the appropriate composition of these movements by taking the hierarchy we have built into account. The analogy to the real object goes as follows. Using the diagram and the 6 DOF axis function blocks, we control the movement of individual drives. For example, rotary and linear motors or pneumatic cylinders. The kinematic relationship tree, as in case of a real object, defines the physical connections between individual mechanical parts. Just like the lift frame is pivotally attached to the body, the frame system is connected to the body system. The choice of the type of connection, rotary, linear or mixed, and the axis in which we move the system is made on the diagram by connecting the control signal to the appropriate input of the 6 DOF axis block. Of course, you can decide against using only one control signal in the 6 DOF axis block. For example, in systems such as mobile robot riding on a flat surface, or the forklift shown earlier, only one 6 DOF axis block can be used to control the X and Y axis and Z rotation axis at the same time. It is an intuitive approach in this case because only one solid, the body, moves in two axes on one plane and can make turns in the vertical axis, which means that it has 3 degrees of freedom. Another thing we mentioned in the previous part of this course is the placement of coordinate systems in a way that they form a kind of framework of our structure. This is not necessary, but it makes our design more eligible. Let's see the same forklift model with shifted coordinate systems. The result is the same, but the location of the systems is non-intuitive and increases the chances of making a mistake while building the model. The position of the coordinate system's center moving in a linear motion is not important, but the position of the center of the systems moving in a circular motion is indeed relevant. We can move the rotary axis in the axis of rotation but we cannot move it beyond this line. Please note the wheel movement. Let's move its y-axis along the axis of rotation. To do this, we must temporarily turn off the simulation of the visualization and function block diagram. Detach the tire from the coordinate system, move the system, reconnect the solid to the system and run the simulation. First in a visualization, and then on the diagram. The solid still moves properly. However, after moving the system off the axis of rotation, we get an incorrect movement. Now let's do a similar experiment with linear motion. The screen shows a block moving on the guide along the y-axis. Now let's change the coordinate system, for example in the y-axis. We can see that it moves similarly as well. Now, let's move it in the x and z axis simultaneously. Our forklift is still moving properly. Let's get to the subject of coordinate systems control by doing a simple exercise. We will now open a new project and insert a coordinate system into it. Let's set it at a position of 100 and 200. Insert the 6DOF axis function block into the diagram to control the position of the associated coordinate system. Let's connect it with our system now. We will want to move it in the x and y axis and rotate in the z axis. Therefore, we will connect 3 sliders to their appropriate inputs. Let's give them names associated with their functions and define ranges of variability. The linear position in the x-axis will be changed in the range from -200 to 300. and in the y-axis from -100 to 100. Rotary motion in the z-axis will be limited to the range from -90 to 90 degrees. At this point, we remind you that the angle of rotation is set in radians, so we will insert a block converting degrees to radians into the diagram. We put the values of our signals into the VR1, VR2 and VR3 registers. We will be able to observe them in the status monitor. After running the simulation, first in the visualization and then in the diagram, we can change the values of the registers controlling the position of our system by using the sliders. At the same time, we can observe the values of these registers on the status monitor. The location of the system is the sum of the values set in the Properties window in the 3D view and the values at the 6DOF axis block inputs. The values from the Properties window set our initial coordinate system location. We can change them while the simulation is turned off. These values are the local position of our system in relation to the system to which it is connected. Each system is either associated with another system created by us, or, by default, with the main coordinate system. However, the values at the 6DOF axis block inputs are used to control the position of the system during the simulation. The grid lines on the coordinate system are spaced every 100 mm. We can check the position of the system depending on the value of the control signals. We encourage you to experiment some more with this system. In this example, we use the slider blocks to manually change the register values. Let's disconnect the sliders from our block. We will insert the VR1, VR2 and VR3 registers as value sources directly connected to the block. We can directly insert values from the sliders into the registers or modify them, for example by entering some mathematical dependencies. Let's bind the y position with the x position by introducing a linear dependency block between them. Now, let's define the dependency parameters. We can now eliminate the axis slider and control only the x-axis slider. The y-axis will move accordingly to the defined mathematical relationship. We can see that this function block diagram is used to control the axis movement. Let's create a second independent coordinate system. Let's set it in position where x equals 200 and y equals 300. Let's connect a similar control system to it, but allow changing the position of our system only in the z-axis. The position of the system will be stored in the VR4 register. Let's change the names of the slider blocks, so that we can clearly see what they are used for and which system they control. The systems are not connected to each other by kinematic relationships, so they move independently. The option of moving to a new system is disabled. Therefore, after connecting, global coordinates must remain unchanged. The local coordinates, which values can be seen in the window on the right, will be recalculated accordingly. Let's rotate the axis 1 system in the z-axis by 45 degrees. Let's connect system 2 to the first one. Please note that the rotation is also calculated. This is a fundamental functionality of Simultus. In practice, these calculations are quite complicated, but Simultus does them automatically. Thanks to this, we will have to take care only of controlling the position of the drive associated with a given movement, while Simultus will perform kinematic calculations and take care of where the individual mechanical elements of our device will be located. From now on, by changing the position of the first system, the position of the second system changes as well. In the Properties panel and Status Monitor, we can observe the values of local positions of both systems. At this point, we again suggest you building a similar system and experimenting with changing the position of both systems, in the properties of the 3D view and in the diagram as well. Bear in mind that the initial values of the system position can be changed only when the simulation is turned off. Let's return to creating the control system for our 4-axis module. Let's insert 4 6DOF axis blocks into the diagram. Let's assign them to appropriate coordinate systems. Ultimately, we want our module to be controlled by Phatex PLC. We will deal with this in the next parts of the course. Now, insert the drive models into the diagram and connect them to our device. Function blocks of models of typical drive components can be downloaded from the simultus.pl website. They can be found in the online help, accessible from the top menu in the Support tab. In this chapter, you can also learn about the operation of these blocks. In the first part of this course, we showed you how to import user blocks. Our device consists of 3 axes moving in a straight line and 1 rotary axis. Therefore, we need to download the function block for the linear model and the rotary model. In our example, this has already been done, so we will insert the appropriate blocks into the diagram. We connect the function block to the appropriate coordinate systems and specify their input parameters. A detailed description of the drive model inputs and outputs is also inside the function block. We can see it by double-clicking on the block. The y-axis will be positioned in the range from 0 to 500 mm and x-axis in the range of 0 to 1000 mm. According to what we have established, the z-axis will move in the range from 0 to 150 mm. And the rotary axis in the range from -360 to 360 degrees. Now let's switch to the 3D view. The x-axis is set to the positive end position, that is 1000 mm. This is how the model was created in the CAD program. We will show you how to change the settings of this element in Simultus, without making changes to the source project. Once we have configured our device's kinematics, where the solids of our model are connected to the coordinate systems and the relationships between the systems are defined, we change this position in the Coordinate System Properties window. Let's move the x-axis by 1000 mm in the negative direction. Naturally, we set any other starting position. Along with the x-axis system, all the elements connected to it have moved. Both other coordinate systems and all mechanical elements as well. Referring to what we talked about a moment earlier in this part of the training, we simply change the initial settings of our coordinate system. Let's set the frequency of the simulation. The instruction of how to calculate it is written in the description of function blocks. Let's specify in which register the position of each axis will be stored. Let them be registers from VR1 to VR4. Now, insert the slider function blocks into the diagram. We will use the sliders to change the position of the axis. Let's set their ranges of variability the same as the ranges of axis positions. Let's also give them intuitive names associated with the axis names. Set the maximum speed to 500 mm per second for the linear axis and 300 degrees per second for the rotary axis. Another input allows setting the motion speed scaling. Let's connect a slider to it. The signal from this slider will be connected to all drives, so that we can set the speed of all drives at once. We will still control positions with the help of sliders. Now, however, the slider will control the set position of the drive, which will move our system in the right direction to the set position at the set speed. Let's use a joint switch to switch on all drives simultaneously. Let's start the simulation. First in the visualization and then on the diagram. We can now control the target position of our module in 4 independent axes. Let's set the speed to 20%. Now we can see more clearly that by moving the slider, we change the set value of the module position, which slowly moves to the target position at the set speed. In the limited positions, the limit switch signals are activated. And when the set position is reached, the in position signal is activated at the function block output. We can use these signals in our control system. We suggest that you make a similar model yourself before proceeding to the next part of this training. We invite you to the next part of this training, in which we will show you how to connect our system with a FATEC PLC.